Hello friends, good morning. In the generator topic, so far I have explained the phase fault protection of the generator stator as well as internal fault in the stator of the generator. Today I will discuss the stator earth fault protection. First I will discuss the unrestricted earth fault protection. This is the scheme for the unrestricted earth fault. This is the generator. I have shown three phases: IA, A phase, B phase, C phase. Currents are IA, IB, and IC. This is the neutral point of the generator. This neutral point is grounded through some resistance. Why this resistance is used for neutral grounding, that I will explain afterwards. So in unrestricted earth fault protection, we are using three CTs, one for each phase, and the relay is connected in the residual circuit of the relay, residual circuit of the CTs. So this is connected in the residual circuit. R is relay. It can be of instantaneous type or it can be IDMT type, high set instantaneous relay, or it is not instantaneous relay or IDMT relay. Now relay current IR, if you look at this diagram, then it is phasor sum of IA, IB and IC. In normal condition, this phasor sum is 0 because we are considering balance condition and ideal condition, healthy condition. So IA plus IB plus IC will be 0. Therefore, no current is flowing through this relay and relay is not operating. Now let us say earth fault takes place not on the generator but after this generator somewhere else. Say this is F1, that is earth fault. It is not on the generator. So when earth fault takes place, it is, I shown this in C phase. So this balance will be disturbed. So IA, IB plus IC, that will no longer be 0. And therefore, this IR, that is current, is flowing through the relay and relay operates. It means it is operating for the earth fault beyond generator also. Now if we look at the generator earth fault, F2 is fault in C phase of the generator, it is earth fault. In this case, again IA plus IB plus IC will no longer be 0. So IR will be there and this IR will cause the relay to operate. So this scheme protects the generator against earth fault. But this also operates for the fault which are not on the, this also operates for the faults, earth faults which are not on the generator. Therefore, this scheme is called as unrestricted earth fault protection of the generator. Unrestricted means it is not restricted to the generator. Second is restricted earth fault protection. Now if you remember the stator phase fault protection scheme, that is merge price protection scheme. In that scheme also I have shown a resistance and the connection scheme, that is 3 CTs are on this side, 3 CTs are on this side, then they are connected through the relay operating coil as well as restraining coil of the differential relay, percentage differential relay, and I have shown a resistance in the neutral wire. So that also protects the generator against earth fault, but against the earth fault which are taking place on generator winding only. So that is called as restricted earth fault protection. Why restricted? Because that protection is providing protection to generator earth fault only, that is restricted to the restricted area. Therefore, that is also called as restricted earth fault protection. Another scheme which is also called as balanced earth fault protection of the generator, that is also restricted to the generator, that I will explain now. Now let us consider this scheme. This is called as balanced earth fault protection, that is also restricted for the earth faults on the generator only. Now in this scheme, we are using 3 CTs like this. One CT we are using in this neutral grounding circuit and these CTs are connected like this. So at this point we are connecting the relay. Now current I1, that is equal to IA plus IB plus IC. This current is IE, so I2 is equal to IE, and relay current is I1 minus I2. Now first consider normal condition. Under normal condition, IA plus IB plus IC is 0. So I1 is 0. Under normal condition, as IA plus IB plus IC is 0, there will be no current through the earth circuit, that is neutral circuit. So IE is also 0. If both are 0, so relay current will be 0. The relay is not operating. That is normal condition or healthy condition. Now second condition, we consider external fault. The fault which is not on the generator winding, external earth fault. I have shown this on phase C. So in this condition, the earth fault current will flow through this point. So that current is also flowing through this CT. So under this condition, this balance will disturb, and current, let us say it is IF1. So I1 will be equal to IF1. Now this earth point, let me show the earth point. This is earth point, and this earth point, they are connected. So what is happening? The fault current which is flowing through this fault, that is also flowing through this residual circuit. The same current is flowing through this circuit. So if we consider this current as IF1, this current will also be IF1. So IR will be IF1 minus IF1, that is 0. So for external earth fault also, this scheme or this relay is not operating. So it is not unrestricted earth fault protection. Now let us consider the fault which is taking place on the generator winding, earth fault on the generator winding F2. Now fault has taken place at this point. So fault current will flow to the earth like this. This point and this point, they are connected. It is flowing like this. Now remember, now you can see in the diagram, this current is not flowing through this CT. It is flowing through this CT only. So if you consider this current as F2, then this IE will be equal to IF2, and this is equal to I2 is equal to IF2. That is flowing through this relay, and through this relay, so from this side, it is not same as IF2. Therefore, current imbalance is there. So I1 minus I2, that is not equal to 0, and relay current is flowing, and therefore the relay operates. Again, I will repeat, this earth fault, we can show earth fault current like this. So if we denote this by IF2, this IF2 is flowing through this CT. So I2 will be equal to IF2. This I1 will not be equal to IF2. Therefore, relay current is not equal to 0. Therefore, this relay is operating. So you can see here that relay is operating for the earth fault on the generator winding only. That is, this protection is restricted for the earth fault on the generator. You can also say this as restricted earth fault protection or balanced earth fault protection. Now let us see how the setting of this relay is provided. Now let us come to the setting part of this relay. Important thing is the relay setting is not too sensitive. Now let us see what is the reason the relay setting is not too sensitive. This relay setting is not too sensitive. Now through this relay, the residual current is flowing from this side and earth current is flowing through this side. Under normal condition, when there is no earth fault, it is normal operation and it is balanced condition. This I1, that is IA plus IB plus IC is 0. This I2, that is IE, is also 0. But this is ideal condition. But in practice, or a practical condition is, there is some unbalance. So IA plus IB plus IC is not equal to 0 even when there is no earth fault. So under this unbalanced condition, some current is always flowing through this residual circuit. As there is no earth fault, this current is 0. So current, unbalanced current is always flowing through this relay. If relay setting is too sensitive, then due to that unbalanced current, the relay will trip. Therefore, relay setting is not too sensitive. Now let us take one example. Let us say pickup of the relay. This relay is set as 0.5 2 ampere. It is set as 0.2 amperes. Let us say CT ratio is 1000 by 1. Let us say primary current in all these three phases under balanced condition is 1000 ampere. Now there is some imbalance. Now due to some imbalance, let us say this primary current becomes 20 ampere. Means IA plus IB plus IC is not equal to 0. It is 20 amperes. So corresponding secondary current will be 1000 by 1 is the CT ratio. So for 20 ampere, it will be 0.02 ampere. So under normal condition, 0.02 ampere current is flowing through this relay. But it is less than the relay setting, therefore relay is not operating. That is under normal condition. Even when there is imbalance, the relay is not operating. Now let us say some fault takes place outside this generator. It can be phase fault, it can be phase to ground fault, it can be three-phase short circuit, line to line fault, or any type of fault. So due to that fault, the current will increase. Let us say this current on primary side becomes 20 kiloamperes. That is fault current. So 20 kiloamperes is the fault current. So through primary of this CTs, current will be 400 amperes. This 400 amperes is the imbalance current. The corresponding secondary current is 0.4 ampere. That is higher than pickup of the relay. So relay will operate. So even when there is no fault on the generator winding, no fault on the generator winding, due to external fault, some imbalancing is there, already there, therefore the relay is operating. That is the reason why the sensitivity of this relay is not too high. So relay pickup is selected somewhat higher. Normally it is 10 to 20% of the rated current of the generator. 20% of the rated current of the generator. So this is first point. Now let us see what is the purpose of connecting this resistance in the neutral grounding circuit. Now consider what takes place at the extreme end of this winding. So this will be short circuited like this. Now if resistance is not there, then this short circuit current will be limited by the resistance of this winding only. That resistance is too small. Suppose 1000 volts is the generated voltage, 10 kV is the generated voltage. So 10 kV divided by 10, suppose 10 ohms is the resistance. So 10 ohms I am considering on the higher side. Let us say its impedance is 5 ohms only. Then 10 kV divided by 5 ohms. The current will be very high. And to limit this current to safe value, we are inserting some resistance in the neutral grounding circuit. I will repeat. If we are not using this resistance, then during earth fault, the earth fault current will be too high. That will be dangerous for the generator. So in order to limit that current, we are using resistance in the neutral grounding circuit of the generator. Third point is, now earth fault can take place anywhere in this winding. Suppose earth fault takes place at the extreme end of this winding. Let us say this generator is generating 10 kV. So if earth fault takes place at this point, then from this point to this point, complete winding is coming into picture. The generated EMF will be 10 kV. If earth fault takes place at the midpoint, then from this point to this point, the EMF we consider will be 5 kV. If earth fault takes place, let us say, at the point where only 10% of the number of turns are coming into picture, because generated EMF is 5Z NP by 60A. So N is number of turns. So suppose only 10% turns are coming into picture, then generated EMF will be reduced to 10% only. So in place of 10 kV, generated EMF will be 1 kV. Generated EMF will be 1 kV. So suppose this resistance is 10 ohms and fault takes place at the extreme end, neglecting the resistance of the winding, the current will be 10 kV divided by 10 ohms. If it is at the midpoint, it is 5 kV divided by 10 ohms. If it is at this point, it is 1 kV divided by 5 ohms. We can see that as the fault point, that is earth fault point, is shifting from extreme end towards the neutral end of the winding, then the earth fault current is reducing. The earth fault current is reducing. If for the same generator, if we increase the value of this resistance, then also the earth fault current is reducing. Now, at some point, if fault takes place, normally that point is in between 10% to 20% of this winding. The current which is flowing through this earth fault circuit becomes less than the pickup of the relay. And if this becomes less than pickup of the relay, then relay is not operating. Therefore, this type of scheme is protecting only certain percentage of the winding away from the neutral point. Normally this percentage is 80 to 90%. So this restricted earth fault protection as well as balanced earth fault protection is protecting only 80 to 90% of the winding away from the neutral end, because we are using neutral grounding resistance. This neutral grounding resistance is also necessary to limit the fault current when it is taking place at the extreme end of the winding. So you can say that we need some extra protection, extra relay, additional relay to provide protection to this 10 to 15% of the winding from the neutral point. So first I will derive the expression for showing the percentage of winding protected in terms of generated voltage, pickup of the relay and resistance of the winding. Now here I have shown winding of one phase only. This is neutral grounding resistance. Let us say X is the, or percentage X is the percentage of winding protected away from the neutral point. V is generated voltage, that is between phase and ground. So we have to consider phase voltage. Is remember here we have to consider the phase voltage. Is relay setting. So obviously this relay setting is from the secondary side of the relay. But here, as we are considering this voltage, this point from the secondary side, so this will be, we are considering from the primary side. So this will be relay setting from the primary side of the relay. And R is neutral earthing resistance. Now consider the fault at this point, that is at the point where from the neutral end for which the protection is not secured. So our fault is taking place here. So let us say current is I. So from this circuit I will be equal to 1 minus X. We are considering this point, number of turns is equal to 1. So 1 minus X is this part multiplied by V, that is the voltage generated, divided by R, that is the current flowing through this relay, through this circuit. Now if this current is greater than relay setting, then only the relay will operate. Now consider the threshold condition. So this will become equal to Is. So 1 minus X will be equal to Is multiplied by R divided by V. So if we consider in terms of percentage, then percentage, this will be multiplied by 100. So percentage of the winding unprotected. Here percentage X means percentage of the winding protected. So 1 minus X will be percentage of the winding unprotected will be equal to Is into R divided by V into 100. So X is percentage of the winding protected. So formula is percentage of winding unprotected is equal to Is. This we have to consider from the primary side of the CT multiplied by R, that is neutral grounding resistance, divided by V, and this will be phase voltage and not the line voltage, multiplied by 100. So this is the formula used for computing the percentage of winding protected when we are using balanced earth fault protection or restricted earth fault protection for the stator earth fault protection of the generator. Now I will discuss how the remaining portion, that is this portion of the winding is protected. That is called as 100% earth fault protection of the generator. This is the scheme for 100% earth fault protection. Generator winding, neutral point, grounded through resistance, and in this case a transformer is used for grounding the generator. This is called as coupling transformer also called as neutral grounding transformer. Now in the secondary of this transformer, two devices are connected. One is N, that is measuring device. Second is A, that is signal source, which is generating signal of 12.5 Hz. 12.5 Hz. Now these signals are injected through this transformer into the generator winding. This is the generator structure of the generator winding. Basically, winding consists of R, L, C parameter. R and L will come in series and C in parallel, like this. So this earth point, that is core of the or body of the generator. This is the winding R, L and C. So this signal is injected like this. Now in normal condition, the magnitude of this signal will be this. Whatever is the magnitude that is measured by this device. So in healthy condition, this injected current will flow through this capacitance up to last point and through the resistance. Means complete impedance of the winding is coming into picture. Now if earth fault takes place away from the neutral point, then the signal magnitude will increase, but it will not increase drastically because this complete impedance is coming into picture. And we don't bother about that because that part or that fault will be covered by the restricted earth fault protection or balanced earth fault protection. Now if fault takes place near to the neutral point, this is neutral point of the winding. Let us say fault takes place at this point. This is short circuit. So this injected current will flow through this short circuit. So suddenly the magnitude of this signal will increase. That is detected by this measuring device and that will trip the associated circuit breaker and the relay. So this is how the protection is provided to first 10 to 20% of the winding from the neutral end, and remaining portion is covered by the restricted or balanced earth fault protection. So this is all about the stator earth fault protection of the generator. In my next class, I will take few numericals on this restricted earth fault protection of the alternator. Friends, if you feel this video lecture useful, then please like it, subscribe to my channel, ask your friends, colleagues and your juniors to subscribe to my channel for upcoming video lectures on high voltage engineering and power system protection. If you want to make efficient and effective use of your time, then read my book on time management. The link for the book is given in the description box. I have launched a useful course for the students on UDEMY. This course is very useful for the students who are preparing for the competitive and entrance exams. The link for the course is also given in the description box. Thank you.